So moving on, for the next lesson, we'll talk about gamma, which is the derivative of delta with respect to s, or the second derivative of c with respect to s. So gamma is the rate of change of delta. So I can write that as the partial derivative with respect to s of delta, and delta is the partial derivative of c with respect to s. So this is just the second derivative of c with respect to s. But again, the way I'm going to compute it, since I've already computed this derivative for delta, I'm going to use that as a starting point rather than starting from scratch. So all we have to do, since we already have an expression for delta, is just take the derivative with respect to s of that again. But that turns out to be pretty difficult, because in the last set of slides, we had this three-term expression for s. But luckily, there's a shortcut. So like I mentioned in the previous set, if we look at the second two terms in the square brackets here, I said that those were going to be equal to 0. But that's something we have to show mathematically before we can do it. We did this. I had one example of this before where I actually had plugged in numbers for the Black-Scholes pricing formula, and we went through the work of showing that this part ends up being equal to 0. And now we'll do it in general, so we never have to do it again. So the textbook says that delta is just equal to this much simpler expression than what we've come up with. And finding an expression for gamma is certainly going to be a lot easier if I only have to take the derivative of this rather than taking the derivative of all three terms. So what I'd like to do is figure out a way to show that this expression here is equal to 0. And so when I write something like this, I'm not sure that it's equal to 0. I want to show that it's equal to 0. So you don't want to just write down equal to 0 and then start plugging in things and showing that it's true. What I want to do is start with this without saying it's equal to 0, and just do algebraic manipulations to it until it finally is equal to 0. And then what I'll have is a line of work that starts out from what I'm given and ends with what I want, basically 0. And that'll be an argument that anytime I see this expression in a calculation, I can then replace that with 0. And that's going to save us a lot of work in the next several lessons. And so the strategy I'm going to use is I have one term that has a d plus in it and one term that has a d minus in it. But remember, d minus could be written in terms of d plus just by adding a little bit to it. And so what I'm going to do is try and manipulate the d minus into a d plus, and then there will be some stuff left over. And hopefully when I factor out the stuff that's left over, it's going to turn this second term into the first term. And if both of those terms are the same, then when I subtract one from the other, I'm going to get 0. So phi of d minus is equal to 1 over the square root of 2 pi e. So I'm using some different notation here just because it gets really small if I have everything in the exponent. So exp as a function, so exp and then something in parentheses, that means exactly the same thing as e to the power of what's ever in the parentheses here. So this is 1 over the square root of 2 pi times e to the minus d minus squared over 2. And that's just the exact definition of phi of d minus. And now I'm going to replace d minus in that expression with d plus minus sigma times the square root of t minus t. And that was just my expression for d minus. And now I have this quadratic form here. So I'm going to expand that. The first term, I'm going to end up with a d plus squared over 2. So it's pretty clear that that's going to get me a phi of d plus. And then hopefully the stuff that's left over is going to be useful to get this result that I'm after, showing that the second term here is actually equal to the first. So this is just what I had on the last bit of the previous slide. So now what I'm going to do is just go ahead and expand this quadratic form here. And so I'll end up with d plus squared minus 2d plus sigma square root of t minus t plus sigma squared times t minus t all over 2. And now I'm going to regroup the terms like this. So basically I'm just taking, oh, got the whole thing that time. I'm just taking this d plus squared over 2 and putting that by itself, because this is now an expression, the 1 over the square root of 2 pi e to the minus d plus squared over 2. That's just an expression for phi of d plus. And then these two terms are what's left over. So the middle term that has a 2 in the numerator and in the denominator. So those are going to cancel each other out. So I've got from my, boy, I can't highlight anything on this slide. I have my phi of d plus from this portion of the previous line. I have e to the d plus times sigma square root of t minus t from this portion. And then I have e, this hasn't changed, I've just written it a little bit differently. E to the minus sigma squared t minus t divided by 2. And now, just a quick reminder of what d plus is equal to. So what I have here is d plus times sigma square root of t minus t. And so all this sigma square root of t minus t is going to do is cancel out the sigma square root of t minus t in the denominator of d plus. So what I have is e to the numerator of the definition of d plus here. So I'll do that in the next line. So all that's happened is this d plus sigma square root of t minus t has just become the numerator of the definition of d plus. And then the bit in the right-hand term is still stayed the same, it's just sigma squared t minus t over 2, and it's negative. So what's going to happen, I have e to the log of s over k. So the exponential and the logarithm, they're inverse functions of one another. It's the exponential undoes what the logarithm did. So this is just going to allow me to take an s over k out. And then when I have an exponential of a sum, that's equal to the product. So this is the same thing as e to the log s over k times e to the r minus q plus sigma squared over 2 t minus t. So this bit here is going to stay in my exponential function, but I'm going to factor out an s over k. And then also using the same property, so here I had a product of exponentials. So this is just going to be the sum of this bit that I've got highlighted and what's inside the square brackets in the lower right here. So that gets this s over k out of my exponential bit, and then leaves me with what's inside the exponential bit here. But now look what's happened. So this sigma squared t minus t over 2 that I've been carrying down the right side of my calculation, I have a plus sigma squared over 2 times t minus t minus sigma squared over 2 times t minus t. So all of that's going to cancel out, and I'm just going to have r minus q, that quantity, times t minus t left. And so now I'm going to go back to using the notation of writing this as exponential. So this is e to the r times t minus t. So that's where this bit came from. And then this is e to the minus q times t minus t. So that's where this bit came from. And now I have an expression for phi of d minus in terms of phi of d plus. And this is the expression that I'm trying to show is equal to 0 again. So I'm going to substitute my expression here for phi of d minus into the second term here. And I get this expression here. And so the first term has stayed the same. but now I have k times e to the minus rt minus t. So that carried over from before. And now I have what's coming from my new expression, phi of d plus s divided by k, e to the rt minus t, and e to the minus qt minus t. But here I have a k and s over k, so that's going to be just s. And then I have an s in the numerator and an s in the denominator here. So all of the strike prices and the asset prices are going to cancel each other out in this term. Then I have e to the minus rt minus t and e to the rt minus t. So when I add those together, I have minus rt minus t plus rt minus t. That's the same thing as e to the 0, which is just 1. So those two parts are going to cancel each other out. So all I'm left with is phi of d plus and e to the minus qt minus t, which is exactly what I had in the numerator over here. And now in the denominator, remember I've canceled out this s here with this s here, so I have the same denominator as well. So when I do all of the canceling here, I've made the second term into the first term, and I'm subtracting them from one another, so I end up having 0. So that means when it's time to actually go ahead and calculate gamma, instead of having to take the derivative with respect to s of this great big formula, I can rewrite that as just the derivative with respect to s of e to the minus qt minus t times capital phi of d plus. And so when I'm taking the partial derivative with respect to s, e to the minus qt minus t, there's no s in that, so I can treat that as a constant, so I can move that across the derivative operator. And so all I need to do is take the derivative with respect to s of capital phi of d plus. And I'll go through this again, but we actually did this already when we were computing delta. So I'm taking the derivative of a function of d plus with respect to s, so I have to use the chain rule. And that tells me that I can take the derivative of capital phi of d plus, and then I have to multiply that by the derivative of d plus with respect to s. And we've already calculated that as well, so the partial derivative of either d plus or d minus with respect to s is just 1 over s times sigma times the square root of t minus t. And then this we've already seen before, with this is the derivative of our indefinite integral, so this is just going to be equal to lowercase phi of d plus. So what I'm left with is the e to the minus qt minus t that I had out here, the 1 over s times sigma times the square root of t minus t that came from the chain rule, so that's in the denominator in the front here, and then the lowercase phi of d plus, which was just the derivative that I got here. And so we now have an expression for gamma, which is the partial derivative with respect to s, of delta with respect to s. And this is exactly the same as the line above it. I've just replaced phi of d plus with the actual definition of phi of d plus. So it's 1 over the square root of 2 pi e to the minus d plus squared over 2. So looks like I missed a little bit because I forgot the squared there. But this should be d plus squared over 2.